Over the past few years, we witnessed an incredible AI revolution, which has been driven by AI chips. In fact, the demand for computing power has never been higher. Meanwhile, the scaling of classical computer chips has slowed. So what's next? While graphene chips, probabilistic computers, and quantum computers are still in the making, light-based computers are already arrived. In this episode, I will break down a new light-based computer chip, which is on its way to data center right now, and I can't be more excited about this. Let me shed some light on it. Photonic computers have been in the making for decades. It all started 60 years ago with the development of optical fiber for communication. And over time, we got excellent at sending information with light. Now, if it works so well, why not to use light for computing? In fact, researchers have been long working on building light-based computers. By now, you've likely heard this idea that light-based computers are faster than digital computers because light is traveling way faster than electrons. Well, it's true and not true at the same time. Let's take any conventional chip, NVIDIA GPU for example. During computation, there is an electron that travels through a copper wire. And this wire acts as a conductor. And this is how it always works. In fact, the problem here is not the speed of electron, but the medium itself, the wire. When light travels at 300,000 kilometers per second, in this case we are talking about millimeters per second. And again, here it's not a problem because wire is a conductor, so it's full of electrons. So here we can reach speeds way faster than millimeter per second. Now, you see, we can't simply say that photons are faster than electrons. It's way more complicated than this. In reality, the real reason why digital computers are slower than light-based computers, because in digital computers we need to switch from 0 to 1, from 1 and 0. And this switching requires us to charge and discharge a capacitor, and this takes time. And this is where the real slowdown is coming from. I explained this concept much more in details in my previous episode on reversible computing, a great episode. Make sure to subscribe to the channel right now and watch it right after this video. So, by now, we understood that the real slowdown is coming from this switching from charging and discharging a capacitor, which is slow. So, that's where the light-based chips save the day. Because nothing like this is happening in the photonic world. In photonics, we compute data without stopping it. Basically, we are computing as the data is flying by. And this computation on the fly happening in the range of femtoseconds, which is 1 quadrillion of a second. So it's very fast.
The main feature of light is not light at itself, but the main feature of light is that you can realize an analog computer. And this is the difference. It's not so much the light part. When it comes to the math, it's more the analog nature of light that you can natively exploit. That's also why we call it native computing. And the main advantage here is that you can carry out complicated mathematical functions without digitalization.
And that's very interesting. In fact, if we want to perform a simple summation on a digital chip to add up two numbers, we need roughly 200 transistors, those tiny devices all the digital computer chips are built of. So then, when we want to do a square root of this number, we need another 7,000 transistors. And then, when we want to do a Fourier transform on this, we need roughly 1 million transistors. So you see, the more complex function you want to implement on a digital chip, the more devices, the more transistors, the more chip area it will take. What's so interesting? When we want to implement a Fourier transform with light, we can do it on a single optical device. So you get much higher computational density. And you might be wondering, how is this even possible? You know, people who are wearing glasses, if you are wearing glasses, you are wearing every day a Fourier transformator on your nose. And it performs this function using no energy at all. Once you understand this, you can use the same principle to implement such complex operations on a light-based chip using special photonic elements. Just think about it. We can replace 1 million devices with just one optical device. And it's passive, so it means light just passing through it, allowing you to do complex math without spending any energy at all. And the same applies for multiply operation, where on a digital chip we need roughly 1500 transistors. On a photonic chip, we can do it with just one device. So we get much higher computational density. That's the reason why the interest in light-based chips is growing at light speed. In practice, it took many decades since this concept of computing with light emerged, till the time when we figured out how to actually use it for computing purposes. One of the main challenges is that light is really hard to control. It tends to spread out and scatter, and it has taken industry a really long time. But QANT has finally built a fully functional, commercial, light-based computer. Their new computer chip is called NPU, Native Processing Unit, and it's powered by light rather than electricity.
We are already shipping first service to high-performance computer centers. And we've decided on that the first processor generations are coming on the standard interface of the CMOS world, mainly PCI Express. And what we actually deliver to the customer are fully equipped servers, which are compatible with x86 structures. So in the end, you get a server module, you plug in an Ethernet cable, you plug in the power plug, and the system operates.
What's even more interesting, their breakthrough technology relies on a special material they're using, so-called lithium niobate. Essentially, they deposit a thin layer of lithium niobate on top of silicon dioxide, which sits on top of silicon. And this particular material is QANT proprietary technology, which is fundamental for the success of their computer chip in several ways. First of all, it's the only material which allowed them to build all the required optical components in the chip in one material. And this is fundamental for avoiding losses of light, because losses of light results in the drop of accuracy in computations. So we want to avoid it at any costs.
What are the fundamental features of thin film lithium niobate? Well, the first thing is that the modulators, so basically whenever you want to interact with the light, we can realize modulators that can operate in the gigahertz regime, so very fast. We can realize these modulators that no light is lost in the modulators. And the last thing is the switching. So in the end, at the technological granularity level, what you're doing, you're changing the refractive index of the material. Mm-hmm. This can be done only using a voltage. And I know this sounds super technical, but it's elementary, because when you only need to change a voltage, there is no electricity on the photonic part of your processor, meaning there is no heat dissipation, leading again to a very clean signal. And we already talked about that clean signals are fundamental to reach, for instance, an 8-bit precision. So this is why lithium niobate is not just another material. It's basically the fundamental source of success for building a photonic analog computer.
In fact, the QANT chip is the first photonic chip which is able to achieve the accuracy of 8-bit precision. Now, to be honest, what struck me the most about QANT is that they're having their own fab. So they're manufacturing their own chips. And basically they own the entire pipeline from design to technology. Then they manufacture the wafers, dice them, package them, write software stack for them. That's a lot of work. This is a very untypical situation for a startup, especially owning manufacturing, because this is very assets heavy. The question is how this startup is managing it all. And the most important, why? Why do they need this fab?
Light chips, the structure of the light chips are per physical definition, so by the laws of physics, are pretty large. You can't realize a photonic circuit with a 50 nanometer width, because then the light would not be guided. So in that sense, what we have is we have access to a CMOS foundry, an old CMOS foundry from the 90s, and we repurposed it with strategic investments of a few tools to serve for the production of our own photonic chips. So in that sense, yes, it's not cheap, but in comparison to what you need to invest in the CMOS world, it's easy. And this is a big advantage to the future as well, because think about it, there are a lot of outdated CMOS foundries in the world which could be repurposed to build high-performing chips for the AI, next generation AI supercomputers, but using mature technology from the 90s. I mean, this on its own is a production paradigm shift.
This is indeed a paradigm shift. Very interesting example of turning, so to say, obstacle into an opportunity. And seeing all the investments governments are making into the photonic technology and into the photonic fabs, and also seeing all tech giants like NVIDIA, TSMC, AMD going all in, these fabs might have bright future. Let me know your thoughts in the comments. Now, before we discuss how this new light-based chip works, what it's capable of, and how it compares to the state-of-the-art GPUs, for example, have you ever wondered how much of your personal private data is floating around online? Your name, address, even information about your family members. Unfortunately, it all gets out there thanks to the data brokers that spread this information online. And this exposes you to risks of data breaches and, of course, personal security. You've probably heard about cases where databases containing information about millions of users are sold online. And sadly, this is happening more and more frequently. That's where Incogni, the sponsor of today's episode, comes in. Incogni helps you remove your personal data from databases used by data brokers. I used Incogni to remove my personal data from those databases, and it's surprisingly easy. You create an account, give them permission to act on your behalf, and they send data protection law compliant requests to these companies, forcing them to remove your information from their databases. And you can even track the progress of these removals day by day on your dashboard. As someone who values privacy, I highly recommend that you try out Incogni and put an end to annoying spam emails and calls. Use my code INTECH at the link below to get 60% off an annual plan. Thank you, Incogni, for sponsoring this episode. Back to the bright new world. Now it's time to discuss applications and how it compares to state-of-the-art GPUs. And here, honestly, I spent quite some time looking into specs, trying to make apple-to-apple comparison, but it's really challenging. One thing is clear, that this analog photonic approach offers way better efficiency. Just think about it. There is no wires, so no resistance, no heat generation. So these chips require much less power to operate, especially at high frequencies. And here we are talking roughly about 30 times better efficiency compared to the conventional digital chips.
Now, with respect to scalability, I think the fundamental question is, can we compete with a GPU cluster? Because this is in the end what our direct competitor in the present data center is. And to give you a bit outline to the future, so in 2 years from now, we're going to have native processing units, so processors coming on a PCI Express card that have the same performance than a graphic card in 2 years on the AI relevant functions. But on the same side, we anticipate that these systems have a 30x smaller power consumption than a graphic card in the future. Now, what does this mean? If you look on a server, today you can bring 8 graphic cards into one server rack. And then you're at the edge of what's being reasonable in terms of power consumption. We can bring much more cards into the same space, and by that increasing the computational density in the server. And since we still have energy budget left, we can bring much more servers into a server rack. And by this increasing, so this is the forecast of today, and I might be wrong, and it's even better tomorrow, but the forecast says that if we equip one of those servers and we plug the same electricity in as they plug in today already, we can exceed the computational density in the server rack by a factor of 10.
What's even more interesting, according to Qant, their chip is built for both inference and training of AI models. And this is very interesting. Typically we distinguish between 2 different kinds of workloads. A more simple inference, when we have already a pre-trained model, we apply new inputs to it, and we ask to recognize an object on the image, for example, to recognize a fox. And on the hardware level, this typically reflects into performing many multiply accumulate operations in parallel.
And we've decided on that we are fully concentrating on the AI inference and the AI training. So the layout of our chips is always that a chip can basically serve both purposes. So we can run AI inferences, which in the end is fundamentally saying similar to a vector matrix multiplication. And on the AI training, we are basically going a different route because we can, in contrast to what training or how training is established using a CMOS equivalent GPU architecture. But the chip layout is always the same.
And this is very interesting because in order to do training, we need to constantly update the model weights. We need to constantly adjust it to improve its ability to make better, more accurate predictions. And to do this in photonics might be really challenging. As we discussed in the beginning of the video, in photonics, this concept of capacitance or storing intermediate results does not exist. So nothing like in the von Neumann architecture where we have this local memory. In photonics, no storage available. In fact, it works entirely different. Here, the longer we can make the light to propagate through the chip without stopping it, the more we can benefit from the properties of light. Let's say you want to train a neural network. First, you encode your weight into the phase of light. And as the light propagates through the chip, you modify it along the way one by one. And at the output, you get the final value. And only then you convert it back to digital, and then save it to memory. For that, the Qant chip features a small electronic part on top of the photonic engine. And keep in mind that there is this special, fundamental property of light that it can carry a wide range of frequencies within the electromagnetic spectrum. To put it simple, we can encode many inputs, many data at once, at different colors of light, and compute it all in parallel. And this is very attractive when we are dealing with large data sets, like in case of AI applications.
We knew photonic computing is new. We know that we very soon understood that this technology can really turn the AI world upside down. But on the same side, to be allowed to enter the ecosystem, you need to be compatible with the electronical interfaces. So if we had our own proprietary interface, there would only be a minor change that we would be adopted into this ecosystem. And the second one, what was also very clear from the very moment, is that the programmers, the coders of the world, they should not have to change their source code in order to experience the features of our technology, at least in the first instance. And this is why we have a whole architecture that we call LENA, Light Empowered Native Arithmetic. And this includes the photonic world. This includes the electronic world, which in the end is the processor that comes on a PCI interface. But at the same side, we also develop the drivers, the compilers, the interpreters that are then seamlessly adoptable by the libraries that are used from all the programmers out there, from TensorFlow, from PyTorch, from Keras, from ONGs, you name it. And in that respect, it's the easiest way to step into this ecosystem because the customer doesn't have to change anything.
To be honest, I'm really grateful to my channel for this opportunity to talk to the most visionary people out there. And this is a very interesting chip and very interesting startup with a big vision. And of course, there is still a lot of work to be done. But to me, it seems like we are closer than ever to the light era in computing. Let me know your thoughts in the comments, and I would love it if you could share this video on social media with your friends and colleagues. I would really appreciate it. Still, I felt this video wouldn't have been complete without me mentioning another huge transition happening in the industry right now, using light for interconnect. And here we are talking about interconnecting parts of the chip, so chiplets with photonics, as well as moving data between the racks in the data center, so at a large scale. As we've just discussed, light has a much higher bandwidth, or if you want, a much higher capacity, because here we can access frequencies in the terahertz range, and that's a lot. Of course, this attracts a lot of interest from tech giants like TSMC, NVIDIA, Intel, and AMD. Recently, NVIDIA and TSMC have announced a collaboration in this space. They've together developed a silicon photonic-based chip prototype. Interestingly, TSMC is making this project, this innovation, a top priority among all their other R&D projects. And they call it COUPE, which stands for Compact Universal Photonic Engine. This new technology will allow TSMC to integrate optical components closer to the processor cores and combine multiple electrical chips with a photonic engine and fiber optic connections into a single package. And with these, they will come to more compact and more efficient designs. You know, modern data centers are quite complex, and very generally speaking, there are two main parts to it: computing clusters and networking clusters. So when we train a large neural network, we need to distribute this workload across a data center, and typically we try to fit as much as possible into a single cluster. And when we are talking about one of the latest GPT models, which is roughly 2 trillion parameters, this is really a challenge. The thing is, it simply won't fit on a single cluster. It means we will have to distribute it across many of them. And here, the efficiency will come down to the wiring between clusters, to the networking. On this channel, I talk a lot about computing power of a single chip or a single GPU. But at the scale of data center, actually networking and wiring makes a lot of difference. For example, according to Meta, about 30 to 50% of overall elapsed time for AI workload is spent in the network, waiting for the network. Just imagine, what if we could replace all this complex networking with photonic interconnect? Startups like Lightmatter and Ayar Labs are working on solving this problem by replacing all these networking switches with photonics. Ayar Labs, for example, is developing a solution that can be applied both to chiplets and data center networking. Just last December, they closed the $155 million funding round that valued the company at more than $1 billion. And no surprise that NVIDIA, Broadcom, AMD, and Intel were among the investors. So, in summary, all we discussed today points out to the future where light will play a pivotal role in computing.
So for the moment, we are not focusing on quantum computing, if this is the question. It's not because I'm not believing in quantum computers. I believe the future compute ecosystem is going to have a multiple chiplet architecture in my words, meaning you having a CPU, you having a GPU, you're having NPUs from us, and you're also having QPUs, quantum processing units. But what I realized 2 years ago was that the time to a commercial product is way faster if we focus on these analog photonic computers, because we understood them very well, and they're at the heart of a photonic quantum computer. So the mathematical operations that we are using on a photonic space are not so much different to what we've been using when we built quantum computers. But for quantum computers, it's really unclear. You can't predict when you're going to have a system that has an economic advantage, not a scientific one. We always see scientific, all the time we're seeing scientific advantages with every new system, but it's hard to guess when there is going to be a system on the market that has a clear commercial advantage. And on the same side, what we realized is that a lot of computations that were linked to quantum computers can already very efficiently carried out by using an analog computer.
I think in the future, each of the computing paradigms I cover on this channel, whether it's analog, photonic, digital, probabilistic, quantum, or reversible chips, all of them will find its own niche application. For example, for matrix multiply accumulate operations for AI inference, we are likely to use photonic engines. For quantum problems, we will rely on quantum computers. And for problems that require high accuracy, high precision, like banking transactions, will be still done on our classical digital chips. I hope this video lightened up your day. Let me know. And now watch this video where I explain how computing backwards and reversible computing works. This episode got a lot of attention and I got a lot of positive feedback on this one. So check it out. Or watch another episode on probabilistic computing where I explain how we can harness noise for computation. Must watch. Thank you for watching till the end, and I will see you in the next episode. Ciao.